All right, welcome. Today, we're going to tackle a really cool problem from linear algebra. But listen, this isn't going to feel like an exam. Think of it more like a fascinating two-part puzzle that, once we solve it, reveals some pretty beautiful ideas in math. So let's jump in and solve this thing together.
Okay, so here it is, question 5. And right off the bat, you can see it's split into two pieces. Part A is all about vector spaces, kind of the geometry of it all. And then part B completely switches gears to matrices and algebra. It looks like a lot, right? You might be thinking, where do I even start? So let's lay out a clear path to get us from here to the solution.
Here's our game plan. First, we're going to dive into part A, that journey into vector spaces. To do that, we'll need a powerful tool, Grassmann's formula. Then, we'll pivot to part B and unravel that matrix enigma. We'll uncover a really surprising connection between them, and then, at the very end, we'll zoom out and see what the big picture is all about.
Let's get started with that first piece of the puzzle. Part A is all about understanding these abstract things called vector spaces. Really, it's about figuring out their size and how they fit together. You can think of us as explorers, trying to map out some unknown territory in a four-dimensional world.
But before we start exploring, we need to know the lingo. First up, subspace. What is that? Well, just imagine a perfectly flat sheet of paper. That sheet is a 2D world, right? But it can exist inside our regular 3D world. That's a subspace. It's just a vector space that's living inside a bigger one. Next up, dimension. We all know about 1D, 2D, and 3D. In linear algebra, it's basically the same idea. It tells you how many different directions you can move in, or your degrees of freedom. It's the most fundamental way we have of measuring the size of one of these vector spaces.
So this is the information the problem gives us. These are our clues. We're told how the subspace W is built and what the intersection of U and W looks like. And we're also given a handful of vectors that live inside of U. Our job is to use all these little pieces to figure out the size of U plus W. Okay, so we've got all these clues, all these little bits of information, but how do we actually combine them to get an answer? Well, for that, we need a special tool, a sort of master key that connects the dimensions of all these subspaces.
And here it is. This beautiful, elegant equation is called the dimension theorem, or sometimes Grassmann's formula. It shows us the exact relationship between the sizes of two subspaces, their sum, and their intersection, the part they share. This formula is the absolute key to unlocking the first half of this puzzle.
With that formula in hand, our strategy is actually pretty straightforward. We're just going to break it down. We'll use our clues to find the dimension of W, then find the dimension of the intersection, and then find the dimension of U. Once we have those three numbers, all we have to do is plug them into the formula. Easy enough, right?
So after we do a little bit of work behind the scenes, checking if those vectors are linearly independent, which is how we find the dimension, this is what we get. We find that the dimension of U is 3, the dimension of W is 2, and the dimension of the space they share, their intersection, is just 1.
And now for the satisfying part. We just take our numbers and plug them straight into Grassmann's formula. So, the dimension of U, which is 3, plus the dimension of W, which is 2, minus the dimension of their overlap, which is 1. That gives us 4. The dimension of the sum of these subspaces is 4. And just like that, part A is solved.
Okay, one puzzle piece down, one to go. Now we switch gears completely for part B. We're leaving the sort of geometric world of vector spaces and diving headfirst into algebra. Here, we're faced with a little mystery involving two matrices we know nothing about, A and B, that are tied together by a couple of equations.
These two equations are all we have to go on. Now, at first glance, they look almost identical, don't they? But there's a tiny, crucial difference. In the first one, you've got B times A. In the second, it's A times B. And if you've worked with matrices, you know that little change in order, well, it changes everything.
So our mission, should we choose to accept it, is to use these two clues to figure out the secret relationship between A and B. It's going to take a little bit of clever algebra, but let's see if we can manipulate these equations and force them to tell us the truth.
Okay, so the first thing we should do is look for a connection, a bridge between our two clues. And there it is! See how both equations can be rewritten to equal negative a squared? Well, if BA minus I equals negative a squared, and B minus AB also equals negative a squared, then those two things have to be equal to each other. This is great because now we've combined our two separate clues into one much more useful equation.
Now for a little bit of algebraic tidying up.
Our main goal here is to learn something about matrix B, right? So it makes a ton of sense to get all the terms that have a B in them together on one side of the equation. We just do a little shuffling and we get this much cleaner statement right here, with all the B's on the left and the identity matrix I on the right.
And this is the first big aha moment. Look at the left side of that equation. We can factor the B out, and what that leaves us with is B multiplied by some other matrix stuff in parentheses, and the whole thing equals the identity matrix I. Now think about it. Anytime you have a matrix that, when multiplied by another matrix, gives you the identity, that is the definition of an invertible matrix. We just proved B is invertible, and we did it without knowing a single number inside either A or B. That's pretty cool.
So why was that discovery such a big deal? Because knowing for a fact that B has an inverse is a total game changer. It's like unlocking a new move in a video game. We can now multiply by B's inverse to simplify our equations in ways that were completely impossible before.
And after we use that new power to do a little more algebra, all of the complexity, all of the messiness, it just melts away. And we're left with this shockingly simple and elegant conclusion that was hiding in there the whole time. A plus B equals the zero matrix. Puzzle solved.
So, we did it. We solved both parts of question 5. But let's just step back for a minute. What's the bigger story here? What did this whole journey from a complicated-looking problem to a super simple answer actually show us? You know, what we just did is a perfect example of what mathematics is really all about. It gives us the logical tools we need to cut through what looks like a complicated mess and find the simple, elegant truth that's hiding underneath it all. It's about finding order in the chaos.
So here's what you should really take away from all this. First, always break down big problems. We tackled part A and part B separately. Second, you have to know what tools to use. Graspin's formula was our key for the first part, and the idea of invertibility was the key for the second. Third, you just have to trust the logical step-by-step process. And finally, remember this, those big aha moments, they don't just appear out of thin air. They're almost always built on a foundation of small, careful, logical steps.
And that kind of leaves us with a final question to think about. The exact same kind of structured thinking we use to solve this puzzle can be applied to, well, almost anything. It's a way of looking at the world, a method for finding the simple rules that govern complex systems. So what hidden patterns are just waiting out there for you to discover? Thanks so much for joining me for this breakdown. If you had fun solving this puzzle with us, do me a favor and hit that like button and subscribe for more explainers like this one. We'll see you next time.